when we look at a process on a PV diagram, like this one, we're going from state A to state B. Remember, the state of the gas is defined by pressure, volume, number of moles, temperature. That defines the state of the gas. And when we move from point A to point B, we can go quite a few different paths. And what's interesting are these four. These four are the ones we like to focus on because they help us see what's going on, and there's some interesting aspects to these. Isobaric, constant pressure. Isochoric, constant volume. Isothermal, constant temperature. Adiabatic, no heat flow. So let me just tell you what that means real quickly. For the constant pressure process, what would that look like? If we were moving on a PV diagram from point A to point B at constant pressure, it would look something like that. Right? The pressure is not changing. We're moving from point A to point B without changing the pressure, a constant pressure process. If we were moving a constant volume, you can probably figure out what that's going to look like. Something like that, right? A vertical line. The volume is not changing, pressure would be. Isothermal, that's not as intuitive what that looks like, but in order for the temperature to remain constant, it follows a path that looks something like this. The pressure and volume have to change in such a way for the temperature to remain constant that you get a curve that looks similar to this one. And the adiabatic process, you also get a curve. I'm going to sort of overlay it here, maybe. And I'll use a different color. And it's a steeper curve. It looks sort of like that. But we can set up systems that make that happen. How do we get an adiabatic process to take place? Well, there's a couple of ways. One is we can make the process happen so quickly that heat does not have a chance to escape. You can think of that cylinder that we looked at earlier, right, with the piston that moves up and down. If we push the piston in very quickly, the gas would heat up. We're doing work on the gas. But if we do it quickly enough, then the heat doesn't have a chance to escape out of the container to the environment. It stays in there for at least a short period of time. So that's one way we could get this to happen. Another way we could get it to happen is to put a thermal jacket, some kind of insulation around our container, and so that would prevent the heat from flowing out of the container, out of the piston. And as we change the piston, heat would be trapped inside, wouldn't be able to leave because it has a thermal insulator around it. So there are a couple of ways we can do that. And we're going to talk more about these. Isothermal processes, one way we can do that is by submerging our piston into a constant temperature bath, maybe an ice water bath. We put it into the ice water bath, and then we start moving the piston up and down. And as long as we do it slowly, that ice water bath stays at 0 degrees the whole time, and it keeps our piston at 0 degrees. And if we do it slowly, if heat is generated inside the piston, it will leak out, it will transfer out to the ice water bath, and it'll keep the temperature of our system at 0 degrees. It'll keep it at the temperature of the bath. So we can do things like that. All right, so we'll talk about some of those, but let's look at some examples, because what the main thing that we want to do when we start off a problem, we're interested in two things. When we're taking a thermodynamic process from point A to point B, we're interested in two things. We're interested in the states, the pressure, the volume, the temperature at point A and at point B, right? The state of our system at point A, the state of our system at point B. And the other thing that is of interest to us is the process or the path between those 2 points. The change in internal energy of our system as we go from point A to point B. The amount of heat that went into or came out of the system as we go from point A to point B. The work done on the system or the work done by the system as we go from point A to point B. So the processes, the change in energy, the heat and the work done, and the states, pressure, volume, temperature, for the 2 states. So that's typically what we need to get the result out. We're looking for these things, and then maybe something more interesting after we have these. We'll talk about that later. But I like to make a chart like this, 2 charts, one for the states, A and B, one for the process going from A to B. And once I have these charts, I start filling them in. I put in the information that's given in the problem, and then I start turning through that information and what I know using my ideal gas law, using some of the other equations I have about these processes and knowledge I have about these processes, and then that gets me to the point where I can fill everything in. So let's do a couple of examples.